What's up, guys? Yo. Holy crap. Another year, another DEF CON. And you know what? It's another DNS talk. Damn straight I got a drink. So, man, can't say I really knew what I was getting myself into with that whole break DNS thing. But the DNS root is signed and people keep blaming me for it. More importantly, it turns out that this whole DNSSEC root signing, I got to level with you guys. I pretty much was convinced any kind of DNSSEC stuff was way too much work for pretty much no benefit whatsoever. No, it's actually kind of awesome. And this talk is about why. Let me show you something kind of cool. By any chance, was anyone in this room at like my way back in the day SSH talk? Yes. You guys are the old school. So check it out. It's not like I ever stopped playing with SSH. It's a really common thing when you're managing networks, like in the real world. You're often managing some customer's network. So here's me trying to log into, root at somecustomer.org. And what does it do? It asks me for a password. Oh man, I gotta find this customer's password, call them up, have a notepad. Wouldn't it be great if I could just say, look dude, I'm Dan at remotesupport.org. I'm trying to log into you, root at somecustomer.org. Yeah, it's multiple organizations. Yeah, it's federation. Yeah, it's something we as a security community have been trying to build for a decade. Oh, wait, that just worked. Yes. And what did I have to do server side? Hey server, you allow Dan at remotesupport.org. Done. DNSSEC is a lot more interesting than I gave it credit for. We've been trying to do authentication and federation across domain boundaries for years, and with DNSSEC, with the root signed, we implemented it in about 4 hours. This is kind of cool. So we basically coined something called DKI, the Domain Key Infrastructure. It's basically PKI, but this time it actually works. We can't do DKI. We can't do DNSSEC if it is in fact, as some people have been saying, oh my God, this is going to be a horrible pain to deploy. It's going to take hundreds of thousands of hours and hundreds or millions of dollars. We can't do what I just did if it's going to cost that much. But I get ahead of myself. There are 4 audiences for this talk. 4 groups that I think are in here. The user, the buyer, the builder, and the breaker. If you are a user, if you are someone who just wants your computer to work right and you're here because you're interested in what that means, I think the entire security community owes you an apology. We have been promising so many things for so many years. When you receive an email from the bank, maybe it's just me, maybe you should actually know it came from the bank. Telnetting into port 25 still works. This sucks. So I apologize. We failed you. We ask you too many questions. We make too many demands upon your memory, and we blame you. I was in a session earlier today where all I heard about was how users require education, as if it was their fault. No. We have failed to give you what you need. And it's not because we're lazy or stupid. It's because we haven't had the foundational tools required to deliver a more secure experience. If you are a buyer, and don't be offended if you're not a buyer for the market terms, but let me give you the bottom line. Budgets are going to go up because this stuff actually works. 10 years ago, we tried as a community to deploy public key infrastructure. There was a whole bunch of hype about how this technology would finally free us from passwords. It's 10 years later, passwords ain't gone away. Now, our stuff from 10 years ago did not work, but it's not like we have any less need for strong authentication. Our belief, our hope, is that DNSSEC through DKI is the way that we're finally going to achieve all the promises of PKI. Now, if you are a builder, if you are someone who makes security products, we are all tired of your crap that doesn't scale. How much stuff have you sold that sits on shelves because it worked in the lab, It worked enough for the initial sale. And you ever notice how like 6 months later, the customer doesn't call you back and talk to you ever again? Yeah, that's kind of been the story of the last decade, hasn't it? A lot of crappy products have been shipped. A lot of devices have shipped with no authentication whatsoever. A lot of sacrifices have been made. You know, one of the things you find with SSL certificates is the browsers care and everyone else just says, wow, this is hard, I'm going to turn that off. Half of all certificates on the internet don't even pretend to offer security. There's only about 1 million certs on the net, period. So it's like all the possible internet endpoints, we're running out of 4 billion IP addresses. We don't even have 500,000 secure endpoints. This is a failure. However, it's also an opportunity. It means we can do better. But the most important group here, and I think actually the majority of the people here, are breakers. You know, most people in technology believe code is secure until proven otherwise. Yeah, you all know better. By default, software is pretty much generally going to be broken. You're the community that looked at my demo earlier and said, did he just make DNSSEC pre-auth in OpenSSH? Is Dan crazy? Thank you for noticing. I think it's time we get some work done. There's about to be some huge bets put on DNSSEC. And I'm going to level with you. I don't want to wait 25 years for the next DNS bug. So you know what? We're actually pushing a radical transparency model. Started a company called Recursion Ventures. We're actually playing in this space. Yeah, so we are going to be backing an aggressive and public and open audit of all DNSSEC and DKI technologies. If you're familiar with Justin Ferguson, he is one of the probably top 5 code auditors that I have ever met in my career. He is auditing LDNS, which is the best DNSSEC library on the planet. We are releasing the pen test report publicly. And not someday in the distant future. We are releasing it September 1st, 2010. This should be an excellent starting point for anyone else who wants to bash either DNSSEC or the LDNS library in particular. The authors of the library, NLNet Labs, are fully on board. There may very well be a problem found in DNSSEC, but we're not going to guess, we're not going to hope, we're going to bash on it until we're happy. Now, some ground rules to doing some DNSSEC work. We don't care about not invented here. We can't have religion. We can't afford it. We have an internet to fix. That means we have a problem that's bigger than any one person, any one organization, any one community, or any one country. We don't care about style. Skype's law is basically, you know what? We security people really bungled up the internet in 2001. We kind of froze it in time. You get HTTP and you get HTTPS. And deal with it. I like elegance, I like theory, but I like stuff that actually works. Not just barely. Systems that barely work are barely deployed. Now there's a corollary. We can't care about historical precedent. You know why? Because it's not like it's actually been working particularly well. We're going to have to do things differently. Or, you know, we can just keep failing for the next 15 years. We do care about operations. We do care about that IT guy that actually has to wake up at 3 in the morning if the stuff fails. We are not going to secure the internet by calling people lazy or stupid. To be fair, that does define us as intelligent and industrious. Great for our egos, crappy for the internet. We are not going to win through moralization. Don't wag your finger at someone and think it's going to change anything. You're really not going to win through regulation. Because let me tell you, without naming names, I've seen a lot of certifications and I've seen a lot of compliance programs, and I haven't seen a lot of competence in any of them. We're going to win this. We're going to win this the old-fashioned way. We are going to deliver a better product that works better, works cheaper, works faster, works easier. It is not like the status quo of security is exactly inexpensive. There is better that can be done by actual, genuine people want to run it. What if it's not? What if you don't think of security as something you bash people over the head with? What if you think of security as, man, this is actually kind of awesome? That is the goal of this talk, to show you DNSSEC, for all the hype, wait a second, I can build something with this. So some timelines. 18 months ago, everyone pretty much knew all of DNSSEC was crap from an implementation side. But 18 months ago, we basically said, okay, yes, it's crap, but this protocol that's gone through IETF for 15 years is actually not bad. It can be done safely, securely, easily. Well, we live in the future. We look at what we have, and not just what the work we're doing. We have 3 open source servers that are pretty good. We have 3 commercial servers that are pretty good. And pretty much any company in DNS is basically saying, man, don't worry about it at all. Just tell us what you want and we'll do it for you. This is good. From a market perspective, this means lots of people are in this space. This is a stable technology. I'm just here to tell y'all, they can do what they're doing. This is where it's going. So first off, let me explain DNSSEC to you. It's not actually that complicated. In normal DNS, you ask a question, you get an answer. Or you ask a question, you get a referral. So you ask Alice, hey, what's Jenny's number? And it says, I'll ask Travis. Travis said, go to Travis. Hey, Travis, what's Jenny's number? Says, ask Charlie. You ask Charlie and get apparently the wrong number for Jenny. What is Jenny's actual number? She keeps giving me the wrong one. So with DNSSEC, it's really quite similar. You ask a question, you get an answer and a signature. Or you ask a question, get a referral and a signature. Now, is it really that simple? Mostly. Referrals now contain new keys. Before, you were just told where Travis was. Go ask Travis. He's down by the water fountain. Now you're told how to recognize him. Oh, yeah, he's the skinny white dude in dreadlocks who's, now the new chief hardware officer of Recursion Ventures. So welcome, Travis Goodspeed. Computers can make stronger identifiers than people can, so we use cryptography. But it's just the same. Everyone always says, I don't understand public key cryptography. Look, it's really easy to recognize a face. It's really hard to smash your face to look like someone. That's asymmetric public key cryptography. Done. Is that it? Yeah, pretty much. Okay, there's some magic here and there with, if Jenny has no number. Lies. Records can expire and keys can lead to other keys. But a lot of the magic is optional, more than you'd think. And all of the magic can be implemented in an easily deployable manner. Now, yes, the easiest thing to do is to call up some managed service provider and just say, hey, go do it. But, failing that, I have heard estimates that deploying DNSSEC could take 100 hours of consultant time per domain. Let me show you how we would... I'm not doing a live demo in the middle of DEF CON. Hook up to this network, are you joking? But this is what it would look... You're just going to have to believe me. This is DNSSEC made so easy to deploy, you could do it on stage at a conference. So, first thing that we have, and I apologize that the text is small, first thing we have is your standard little name server. It's got, 10 or 11 domains. They're very small and whatnot, very simple, kind of thing anyone might have. Okay. Step 1, change the port on the DNS server from 53 to 50,053. Step 2, launch Freebird, the Recursion Ventures DNSSEC server. Note the lack of options or configurations or anything. You just run it. Step 3, there is no step 3. You're done. Once upon a time, web servers were very simple things. They ran static documents. You had a file system. Everything you wanted to do, it had to be through there. And if you wanted to do anything dynamic, okay, you ran processes with CGI. You know what? Web services evolved. So are name servers. This thing goes ahead. It dynamically generates the signature. It'll dynamically generate the key material. Now, we're not entirely done. We do need to go ahead and tell, in this case, .org, hey, we actually exist. This is where we are. So this is how it looks. You go. Yeah, let me talk about something else I'm not doing from DEF CON. So we go to GoDaddy, say, hey, I got remotesport.org here. You go to name servers, you hit manage DNSSEC, you paste in this little record, you do a simple lookup, it comes back against the Freebird server, gives you the hash to put in. You say, go ahead and do it. You got to wait 30 seconds, and then you're done. And then it's live, and then it's working, and then you can run end-to-end authenticated queries against remotesport.org 30 seconds later. This is actually kind of cool. So why does this work? Freebird is an online key signer. Like SSH, SSL, and IPsec, it depends on a signing key being available whenever requests come in. There's an alternative where a magic key sits in a vault and you truck it out every once in a while, you alter things in DNS. In our real-world networks, we're changing stuff in DNS all the time. Freebird, for performance reasons, actually has a cache. So when it applies signatures to some records, so a record might be, this IP address is, the IP address for foo.com is 1.2.3.4. Or, I don't know, the certificate for foo.com has a hash of AABBCCDD. Freebird will see responses come back and will sign them so that 1,000 requests for the same name will not cause 1,000 hits to the encryption engine. Now, DNSSEC was designed to allow offline key signing, and that is awesome. The two reasons why this is the case are, first, DNSSEC is old. I mean, DNSSEC was started in the 90s where high-speed processors and cryptographic accelerators simply weren't the kind of things that were available. Also, DNSSEC needs to operate at scale. So it needs to be able to simultaneously support the smallest of the smallest name server to the root operations that have a maximum security requirement to COM, which is just enormous. But not every server should be run like the root. It's a big deal that everyone can be, but that doesn't mean should be. Because the reality is, the biggest thing that made DNSSEC such a miserably complicated thing to deploy was having to do some massive pre-computation phase. When you have some massive preload happen, it turns out empirically protocols get orders of magnitude more complicated. And the best example actually is PGP or GPG. The amount of work that those code bases go into to managing their key rings are literally 95% of what's going on in there, with the other 5% being encryption, decryption, signing, and validation. It's enormous, and by going online, you get rid of the complexity. Now, there's some precedent here. We did not invent online key signing. I mean, look at all those other protocols. DNSSEC has been quietly including support for this design strategy for years. Ben Laurie is the guy behind it, behind at least some of it. There's even another DNSSEC server that does this sort of lazy signing. That'd be Powered DNSSEC by Bert Hubert. What Freebird has is kind of interesting is that it uses the existing DNS framework, whatever it may be, and enhances it with DNSSEC responses. So it's just a proxy. It sits in front of your systems like a lump in the wire, and it signs. That means there's no operational impact. You manage your DNS just like you always have. There's no configuration. There's enough information in a DNSSEC request-reply pair to figure out everything that is needed in terms of the signatures involved. I wasn't sure it was going to end up that beautiful, but it turns out, yeah, it totally does. And it always returns the right answers. So you can have the world's most complicated name server that is like trying to return video over DNS, and I'll still sign it. No problem. Implementation notes. Today it's a UDP port forwarder. You've got to change the DNS port. If you don't even want to do that, sometime in the next week or two, I'm going to implement what's called Linux mangle table support. The name server will think it's sending an unsigned response, but something magic will happen in the kernel, and it'll be like DNSSEC on, DNSSEC off, DNSSEC on. So this stuff is fast. Don't look at me. I just wrote a few lines of code. The Linux kernel developers and lib event developers are awesome. Niels Provost is a badass. With a few hundred lines of code, you can today write a name server that will support 60,000 queries per second on stock hardware. Now, if you want to understand how fast 60,000 queries per second is, only a few years ago, that was all the queries that .com received in the world. So on one box with this API approach, you're able to do what .com was doing a few years back. It's actually quite impressive. Now, we're not going to be that fast because we've got a back end to talk to, we've got to manage crypto, we've got to manage caching, but the experimental evidence suggests we are by leaps and bounds fast enough for all but the absolute biggest thing, and we haven't even tried to optimize. Freebird is open source because you're just going to implement it anyway. We should have code out today, but we wanted to get all the demos done. So if you want a preview of what probably has some horrifying remote code execution flaws, feel and by probably I mean like man. That's not a good use of popen. Seriously. Send an email to info@recursion, and you can make fun of me all night. Code should be out within the next couple of weeks. I am actually planning. Have you guys heard about these Pixel Chi displays by any chance? Fully sunlight capable. I actually got one out of Maker Shed. All I want to do in life is sit by the pool at the Palms, get a pina colada, bust out the netbook, and hack. Like, yes. So that should actually dramatically accelerate development of the Freebird packaging. As a note, this stuff really is the 6 to 18 month timeline, so your mileage may vary in terms of deployments. This is purely so you can understand, wait, this technology is pretty cool. Now, Freebird's doing a whole bunch of stuff I don't have time to tell you about today. I'd be going on for a couple hours if I did. There's a bunch of obscura, there's a bunch of things people have kind of wrung their fingers about DNSSEC. Questions like, how do you handle non-existent records dynamically? How do you tunnel records to the registry.org when, say, your registrar doesn't give you a web interface to be able to put what are called DS records in? What about time? How do you manage rollover and expiration? How do you keep clocks in sync? There's some very interesting problems in DNSSEC around what do you do about time, since everything has an absolute time. What I do have time to tell you now is this. All these problems are pretty easily managed. They took some work, they took some effort, but we've got fixes for all of them. And online, the recursion.com site, the answers will be posted. But I want to focus this talk on, hey, this technology is going to be awesome for your applications. So, okay, towards the domain key infrastructure. Perhaps DNSSEC is easy to deploy, but is it in fact useful? Distributed authentication is only interesting if it provides end-to-end semantics. My desktop to your server, or my phone to your phone, and so on. You might say, but Dan, I know a little bit about this stuff. I heard that all DNSSEC does is secure the link between these name servers that I speak to, but not like me and the actual end server. So what's going on here? Well, it turns out that was the original model of DNSSEC. They actually figured your name server would do all the hard work, and then it would send you a little bit called AD. And AD stands for, nah, it's cool, I checked it for you. It doesn't actually stand for that, but it really does. Look, I like Starbucks. I've known people who work for Starbucks. I like their coffee. I'm not trusting Starbucks to tell me whether it validated the certificate for Bank of America. Not gonna happen. There's no application on earth that's going to alter the user experience based on this little bit of context. Give me the proof or go away. So we have some normal end-to-end modes. First mode is called chasing. When you ask for www.foo.com, you can set a bit called CD, called checking disabled. And what you will get back is the answer and a signature saying www.foo.com was signed by foo.com. And then what do? Well, you go back to foo.com. You say, well, what were you signed by? And it says, well, I was signed by com. And then you say, well, how about you, com? What were you signed by? And it'll say, well, I was signed by the root. And then at that point, you have a chain from www.foo.com to the root. And in this model, you only talk to your local name server. Now, there are two problems with this model. It works about 90% of the time, But that's not enough. A 1 out of 10 failure is still operationally too expensive. The first problem is that it might get blocked by your local resolver. The deal is, in DNS, it's a lot of work to bounce around the internet, to go from root servers to com servers to yahoo.com servers. I mean, it takes some complexity. And DNS was designed in 1983 when such complexity was unimaginable to have on every single computer. So what they did is they said, okay, we'll take this hard work and we'll put them in these magic boxes called name servers. And these magic name servers, they'll go ahead and do all the runarounds. Well, what is happening in this situation is the box that's doing the runaround, not only might we not be willing to trust it to go ahead and do DNSSEC validation, but it may not know how to send us back a little bit of extra information about the key material so that we can do it. In other words, it ain't doing it, and we ain't doing it, so it ain't getting done. And so that's kind of a problem. The other thing that might be a problem is round trips. If I have to keep going back and forth with my local name server, that's actually a lot of round trips, and it can be slow. And as we know from experience, if you make a web browser depend on too many things that are slow, it will just not do what you ask it to. So in general, almost all web browsers don't go ahead and check to see if a certificate has been revoked. Someone's checking if certs are revoked, because apparently there's a couple billion checks a day, but your average web browser is not one of them. Revocation is a bit of a lie in X509. What we're doing about round trip fixing in DNSSEC, and this is a project of Paul Vixie and mine, it's called SuperChase. In SuperChase, when you ask for when you say, hey, give me some signing information for www.foo.com, in SuperChase, it gives you the path all the way back to the root. Why? Because it has to know it anyway. If it was going to do the validation, it knows the chain. I'm just saying, hey, give it to me as well. And so we figured out how to make that happen, and it's pretty straightforward. Doing it's about 10 lines of code in LDNS. Part of the Freebird release is going to include sample code. You just say chaser spooky.navy.mil.org, and you in fact get a path all the way back to root. Done. End to end. Another method is called tracing. Instead of chasing where you go up, tracing you go down. You're basically taking that magic box that does the running around the internet, you're embedding that in random applications with what's called libunbound. Libunbound is the name server built upon LDNS, and it itself is it takes about 3 lines of code in libunbound to do a secure resolve. It's super straightforward and easy. There are some issues. Chief among them, if you have a situation where every device is going straight to the root, you'll cause the root to melt down in a pile of flames. What might make that acceptable, or at least make things better, is if the devices are actually caching information for serious periods of time and only updating the information when it changes. The root information doesn't change much, COM information doesn't change much, and so on. This, by the way, was the problem with DNS curve. Dan Bernstein's brilliant. You guys have no idea how much time I spent arguing that people should do his stuff. However, if Dan Bernstein's approach, the only way to get end-to-end trust was to bypass the local caches all the time, always go to the root, always go to the COM servers. They would have melted down. And of course, those middle boxes, worst at hotels. There's nothing worse than hotel networking. When you're at a hotel, be glad you can go to Google. It's surprising. Hotel boxes will still mess with tracing operations. So, HTTP is the universe's universal tunneling protocol. You can actually do DNS over HTTP. DNS over HTTP basically involves doing GET requests with DNS in the actual URL that is requested. Freebird does implement this. Obviously, you can tunnel stuff over DNS, over HTTP, because everyone tunnels stuff over HTTP. The only question is, what's the performance impact? So, what do you guys think? You think, tunneling everything over HTTP is going to have like a 10% hit, a 50% hit, an 80% hit? Yeah, well, for whatever reason, it seems to be faster. What? Yeah, no, 3,200 queries per second with UDP and 4,000 with TCP. Paul Bixie thinks I'm wrong, thinks there must be something wrong with my tests, and that's okay. You know, the quote goes, being wrong just means the world is more interesting than you thought it was. But even with a significant penalty, super chasing over HTTP should be a, if all else fails, get me this information approach that we need. And so we're actually going to go ahead and start running a DNS over HTTP endpoint on the internet within the next couple of weeks so that the libraries that are out there, if all else fails, can always get stuff resolved. Because that's the only way we're going to get to 100%. Wrapping. So I talked about chasing, I've talked about tracing, I've talked about chasing, tracing, packing. This is wrapping. And wrapping is an idea of this crazy Kiwi by the name of Brett Watson. And what Brett said to me is, you have to be willing to separate the content of DNS from the transport of DNS. Now this was a fairly profound point, and it led to an interesting concept. If you look at X509, X509 certificates always contain hi. This is a certificate for www.foo.com, foo.com that's signed by VeriSign or Thought or GoDaddy or whoever. So there's a chain back from where you are all the way up to some trusted certificate authority. X509 can also contain the DNSSEC chain. SSL's already moving X509, so we do DNS over X509 over SSL. You know what totally passes through hotel mini boxes? SSL. Also, we get really high performance because it's delivered in line without any kind of external query having to happen. Now, to implement this, what you have to do is you have to do just like Superchase. You have to extract all of the keys necessary in order to resolve a zone. And then you have to shove it into an X509 certificate and validate it during the actual certificate validation. Now, this would have been a lot of work for me. So, Adam Langley at Google may very well have sent me a private, unofficial build of Chrome. Yes. That is getting HTTPS. It's got the lock, but when you look inside, that certificate has a DNSSEC chain enabled, full DNSSEC inside of Chrome. What's up? So I want to be clear, this was private, this was unofficial, this does not at all represent a commitment by Google to DNSSEC, DKI, or X509 certificate embedding. This is just Adam and I seeing what was possible. So with that, I think it's a good idea to start talking about actual applications. Where do we implement DKI? What I showed you at the beginning of this talk was SSH, specifically FreeShell, a federated identity system for OpenSSH. It's based on the idea that end nodes should authorize and validate identities and not public keys. You are not P times Q. You are at least an email address. Today, the way that this works on the server is you go to the authorized keys file and you provide a list of email addresses that are allowed to log in. When someone tries to log in, they have a special syntax that they use for their username. That syntax is parsed, and if the declared user is actually someone who could potentially log in on that account, then DNSSEC is queried securely end-to-end to say, all right, Dan at remotesupport.org wants in. Dan at remotesupport.org, if he had the right private key on his system, yeah, we'd let him in. Let's go to DNS to find out what public key to validate. So that's what it is today. Tomorrow it's going to be an actual LDAP backend, sort of like this Fed SSH package out there. And you'll be able to say, let everyone in the support.vendor.com group log into the machines at somecustomer.org. This is going to be very, very nice. Now I'd like to go a little bit philosophical into why this is a big deal. People have been selling what's called federation for years. Federation being the ability to authenticate users outside of your organization. All of the stuff has been terrible. The reason why is we have a couple of choices. Our first choice is end-to-end complexity. That means every company that wants to authenticate someone else has to make a deal with every other company who wants to authenticate someone else. It is end-to-end complexity that gives us things like on Gmail, if you receive mail from eBay or PayPal, then you get special user interface. Why was it one email provider and two possible senders? Because the management load of getting more done was too high. Then there's the problem of risk of the kingmaker. You always have a situation where one group says, all of you, why don't you just trust us? Everyone trusts us, and we declare who is who. It's great and it's wonderful. And it turns whoever is in that position of the centrally trusted person into a monster. It happens every time. And so the final approach, and this is what we see in the existing certificate authority system, is key bleed. No one wants there to be a God, so you end up with everybody's God. It's not any better. What is interesting with DNSSEC is that the DNS root is run by ICANN. And for all the controversy of ICANN, this is a group that is massively constrained. They are constrained by a technology that delegates as soon as possible. They are constrained by politics of the worldwide nature that you cannot imagine. ICANN getting things done is a tremendous amount of work. That is not a bug, that is a feature. That means you have a neutral overseer. Net neutrality began with ICANN, of all places. It's kind of crazy. So what do you end up with? DKI gives us federation that actually works, because you have the trusted root that the technology needs, but you have the controlled root, the managed root, the governed root that the politics require. So what do? We're going to go ahead and manually hack in LDNS or libunbound into each package one by one by one? Well, you know, maybe that might be useful for some things. It's definitely a way to get the best application integration. But you know, Linux and Unix, everything's using OpenSSL. Specifically, the OpenSSL call x509_verify_cert. This is a nice and self-contained library call. What could we possibly do with that? So, another thing we're releasing is called Freeload. Freeload adds DNSSEC transparently to existing applications. If it validates a certificate, we will make it validate a certificate successfully using DNSSEC. There is some prior work. LibVal Shim from Russ Mundy at Sparta will actually go ahead, and it also transparently applies itself to applications, but it does so at the DNS layer. It makes sure that applications get the right IP address. That's nice. There's a million ways to attack IP. I'm sorry, that's just how it is. The other thing that Russ Mundy's code does is it assumes that if you're validating for www.foo.com, obviously you have the foo.com certificate, because when this code was written, the root wasn't signed. With Freeload, Freeload is operating at a different layer. It's saying, look, let's take the software out there that is actually trying to be secure. It's actually trying to make an encrypted end-to-end safe link. Let's take its validation layer, which already has handlers for errors if validation fails. Let's take the validation layer and replace or augment it with the authentication layer of DNSSEC. So for example, you ever gone ahead and used these command line web tools and said curl some address, and you get back, you know, this big error, and the last line, of course, is if you'd like to turn off curl's verification of the certificate, use the -K or -- insecure option. Now think about what this means. At some point they said the -K option, and people missed it. So they have 2 points in the documentation where they say, here's how you turn off the security. That is a system that has failed. Now we're going to go ahead, we're going to LD preload freeload.so, and bam, this is a story all about how my life got twisted upside down. Works glorious. If we go ahead and we turn on debugging, we say export DNSSEC debug equals 1. What we see is a lookup happened to what we call the deliberately incorrect schema. We look up sslabsolute.www.hospitallink.org. It has returned this hash 5E0905B and so on, and that is actually the correct hash of the certificate seen at that address, and validation occurs just fine. So that's all that's happening. You have this silly little value in DNS. It's wrong. We're working on the right way to do it. If you go ahead and you change the value, you make the hash incorrect, poof, curl doesn't work anymore. It's not enough for it to do a DNSSEC resolution. The hashes have to match. We set the information back. We go ahead and we can use curl. We can use wget. The same code, the same configuration works for all the protocols. Now, all OpenSSL apps means all OpenSSL apps. So you've got Postfix as a mail server setup, Postgres as a database, MySQL as a database, Apache. Now, why would it be interesting to alter certificate validation in Apache, which is a web server? We've had the capability in web browsers to do client certificate validation, meaning it's not just the server that has a cert, the client has a cert. But today, really getting a certificate issued by one site or a smart card issued by one company to work anywhere else, yeah, good luck with that. With DNSSEC, it's trivial. You get a smart card, we get a request, it claims to be an email address, you go ahead and find out, so what's the public key associated with this user? And the group that issued the smart card is the group that hosts the public key, and now that public key works on every server on the globe. Works like a charm. Welcome to domain key infrastructure. But I'd like to go ahead and stay focused on browsers. OpenSSL is great, but browsers don't use it. Internet Explorer uses a crypto API, and Firefox and Chrome use NSS. Also, there is no LD preload on Windows. There's just no way to go ahead and hack an API in Windows. So what are you going to do? HTTPS proxying. This is kind of neat, actually. I had no idea this was there. PDP ignored this and put out this thing called httpservers.py. It's based on the work of Azuki Hsiao, Andres Riancho, and Dave Vitale. And basically, the web browser has, since the beginning, had what's called the SSL proxy or secure proxy. And what that does is, it says every time an SSL connection is attempted to be made, please do connect www.site.com:443. Now, this is actually very nice. I mean, this is a channel by which I can see what the browser wants without having to push any code in there. I should really build a proxy. So we built a proxy. It's called Foxy. It is a remote validation proxy for production browsers. Basically what you do is you provide the browser a custom root certificate. So the browser knows, okay, you know, I'm going to trust whatever this random piece of code tells me. When the connect line comes in, we know the domain the browser is expecting to authenticate to. It's pre-declared to us. So we basically gin up a certificate at that point. We allow the connection to come in, and then we hook it up to an SSL connection of our own out to the internet. Now here's the thing. We are not actually going to certificate validate the cert out there. So we don't want to make these connections unless they're good. We're outsourcing certificate validation. We're not disabling it entirely. However, since we're outsourcing certificate validation to OpenSSL, and OpenSSL is running freeload, we inherit DNSSEC for nothing. And just so you see what this means, there's the browser lock from DNSSEC in Internet Explorer. There's the browser lock in Firefox from DNSSEC. There's the browser lock in Chrome. No private build. It just works. Done. Move on. Now here's a neat trick. This is a bad idea of old style. There's something very interesting we can do once we've outsourced validation. It doesn't involve DNSSEC, barely even involves DNS. Wouldn't it be nice if we could bootstrap trust only with a domain name? What if we put the hash in the URL? Yeah, that's not a good idea, but it is actually something that works. So basically what we have here is HTTPS SSL hash bighash.www.pba.org. If you can go ahead, you can actually even extend this to, you can put a hash in front of an IP address, and the server will say, well, I connected to that IP, here is the hash of that IP, I will let it through. There are lots of reasons why this is bad, but if you really, really need to bootstrap something and you don't have any other way of declaring what certificate you want to use, this is actually not the worst way to go. Now, what's funny is this was actually inspired by this old file system called the self-certifying file system. Someone else made this link. It's called SFS HTTP, Securing the Web with Self-Certifying URLs. It was done by some guy, Michael Kaminsky. Michael is my middle name. This was done in '99. There are some scalability issues. What do you do if the certificate is lost? But like I said, there are some situations where I think it'll actually be really useful to be able to say, please bootstrap your initial connectivity. Here's the URL. And by the way, the URL contains the hash of the identity you're speaking to. And hey, it doesn't have to be a good idea. Sometimes it can just be cool. So, around this point, you might be thinking, now is the time to get rid of the certificate authorities. No. The CAs are, in fact, more critical than ever. There are domains, www.bankofamerica.com, procterandgamble.com, and so on. And there are brands, Procter & Gamble, Yahoo Incorporated. Domains and brands are not the same thing. If you go ahead and you look at what the CAs have done to actually offer value, they have gone ahead and done a program called extended validation where they will say, this isn't just bankofamerica.com, this is the Bank of America Corporation. That's great, because that is something DNS is not going to be able to do. Extended validation has some problems. I can't go into full depth. If you want to know more, look at Mike Zussman and Alexander Sodorov's SSL rebinding attacks from Black Hat last year. And the basic problem is EV only protects you against phishing attacks if EV only protects you if the attacker doesn't have a non-EV cert as well. So a bad guy who goes to Lens Certificate Check and gets a certificate for www.bankofamerica.com, he can go ahead and interfere with green bar communication. That's just the nature of the technology. But DKI fixes this. DKI has what we call the exclusionary property. When your DNS domain is registered through Enom, GoDaddy cannot interfere with it. When your X509 certificate comes from VeriSign, GoDaddy can. It's because there's no actual link, no actual forcing function saying when VeriSign's got a cert, GoDaddy can't. But you do have that in DNS. So what you can do under DKI systems is you can say the only canonical certificate for www.bankofamerica.com is the extended validation certificate issued by VeriSign. And any other certificate, I don't care who it's signed by, that cert's not valid. That ends the EV attacks. And while, yes, there are attacks under EV where there are, say, invisible subdomains, things from content distribution networks that load stuff, we can go ahead and we can use the same stuff. It is, in fact, cheaper to deploy a DNS record with those submachines SSL certs than it is to go ahead and get SSL set up on them normally. So exclusion works there too. Before we finish, I do believe that we promised users we would do something about email. Now, I don't know about you guys, but I am sick and tired of trying to find people's PGP keys, and worse, just sort of assuming that what I get back from the key server is valid. Wouldn't it be great if you could securely retrieve them via DNSSEC? Well, we've begun a project. It's called FreeGP, and it actually is porting end-to-end DNSSEC lookups to GPG. You might notice this is a little hideous. I've had to type echo foo, GPG, no default keyring, temp, GPG, random, encrypt, armor, auto keylocate PKI, -r, test@pba.org. It's so user-friendly. GPG really does not want to be patched to do this. It has a bunch of DNS code in it. It's only present on the encryption side. The amount of rework that's going to be necessary to make this happen, effectively, this work needs to be done inside of Enigmail. It's hideous. But, all right, I started it a little. Then I went ahead and looked at anything else. DKIM. DKIM is a scheme for retrieving public keys, not certificates, for domains outside of DNS. It is pretty trivial to get end-to-end validation out of it in terms of So its goal is this mail server and that mail server want to know, okay, Google wants to know it's getting mail from the Bank of America server. The Bank of America server signs all of its mail with a particular private key. Google looks up the public key in DNS, validates the mail, only delivers it if it validates. That's cool, that's nice. There's no real user experience designed into it. Right now it's mostly an anti-spam system. Super trivial to do DNSSEC with it, and IETF is looking at making that happen, but I'm not really a fan. I want there to be a user experience. And the best user experiences out there, and that ain't saying much, is from SMIME. SMIME is the email encryption and decryption buttons you see inside of Outlook and inside of Thunderbird. There claims to be a plugin for Gmail. It doesn't verify. It's dead to me. SMIME has some key management problems. This is an understatement, but of course it has key management problems. It's based on certificates. Even if you have the greatest enterprise CA in the world, meaning you have wonderful systems for sending email and getting everyone in your organization to have certificates, SMIME has a problem, which is some cheap little shop on the internet has root certs, and they will go ahead and ship a cert for any email address if DNS tells them they're supposed to. And you know nothing could go wrong with DNS. So can we fix this? Actually, can we? We are able to hijack OpenSSL because of LD preload. We are able to hijack the browsers because of secure proxy. How are we supposed to hijack Crypto API? The only extensibility point inside of Windows that we could find lets you reject certificates but not allow them. It doesn't let you say accept a certificate that's self-signed. Now we could write an Outlook plugin, but who wants to do that? There's another trick, but you'd have to get me really smashed. Like one beer is not going to do it. So I guess we're hosed, right? Raise your hand if you recognize what this code does. Anyone? I'm just going to hope that it's, byte temp jump size equals OXE9, OX90, 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 OXE3, mem copy jump, temp jump size. There's some virtual protect in there. All right. So API hooking is not just for World of Warcraft anymore. Yeah. Most people use these tricks to hack World of Warcraft. We're going to hit Crypto API in Outlook because, damn it, I wanted it to work that bad. It is possible to inject code into any process to alter how it works. We've built FreeCAPI, which is DNSSEC validation for Microsoft Crypto API. Crypto API has a function called cert get certificate chain. If it returns true, the chain is valid. The call receives all sorts of interesting context about the certificate being validated. I'm not that much of a binary hacking guy. So imagine my surprise to find out when you inject a function with full symbols into a closed source application like Outlook, you get full debugging symbols at that particular point. So here's the certificate in the middle of Outlook with all of its debugging information valid. Awesome. So what are we going to do? So we have this signed email here from dan@thebank.org. Not exactly the most compelling image. Look at those 16 pixels throwing the mark of award of validation. What we're going to do is we're going to add a checker. This is remotedll.exe. It's not like I could have written this manually, but I thought if I'm going to use the World of Warcraft approach, I might as well use the World of Warcraft toolkit. Also, the website is securityexploded.com, and I'm pretty sure this is going to security explode this guy's head. I was in what slides? No. So we're going to go ahead and we're going to inject our own cert get certificate chain into Outlook. And when we do this, well, first off, we haven't done anything with DNS. Certificate validation is attempted. It's a totally valid certificate, but there are problems with the signature. Check the signature button. So we get this big red line. Look at that user experience. Awesome. Now what we do is we go ahead and we take the fingerprint of the canonical certificate, the thing that is going to be used to sign mail from dan@thebank.org, and it's 46OC1BE3. We are going to shove that into DNS, 46OC1BE3. Now, this next time we validate the certificate, this value is going to be securely extracted from the DNS. It is going to match the certificate used to sign that email, and the email will now come back signed. This is now the only certificate in the world from any certificate authority that can be used to sign mail from the bank. That's actually not something we've been able to do before. Never been possible. Now, you shouldn't be that impressed because it's 16 pixels. Who cares? What user's going to give a crap about that? You ever wonder why they're giving you so little visual information? Let me tell you. Under the normal SMI model, we have had so little assurance, so little validation that what we're seeing is legitimate. So what we have is, when the certificate validates, we put a few pixels on. And when it's bad, we're like, eh. We can do better. We can strongly identify email senders now. We can strongly identify the brands. What if that certificate that the DNSSEC was validating, what if that certificate was an EV cert? What if you weren't just getting mail from dan@thebank.org? What if you were getting mail from dan@thebank Incorporated and the green bar experience from the browser actually showed up in email? We would be able to tell users legitimately, when you receive an email from the bank, someday soon, you will know it came from the bank. Conclusion. Oh, go ahead. So, DKI is coming. Get on board or don't, but here's what we're delivering for you to see. We have shown you that DNSSEC can be deployed in 2 minutes. We have shown you that we can achieve end-to-end security no matter how messed up the hotel network happens to be. We have shown you federation for probably good federation for the first time in your career. We have shown you how every OpenSSL application can use this technology using a simple LD preload. We have shown how real browsers are going to have real useful experiences with this tech. And we've shown you how certificate authorities and extended validation are going to combine with DNSSEC to finally give us secure email. That is what I've got. Get to work building, get to work breaking.